My name is Todd Sacktor, and the next session is going to be on learning and memory. So I brought along some mementos from my life. So this is my mother's dinner bell. So this is from mid-century modern, Danish probably, so from the 1950s. And this will be for the 7-minute and 30-second time point. Now this is my great aunt. So my great aunt was an English school teacher in the Bronx who rose up the ranks to become head of the entire English department for the entire New York City system in the 1940s and 1950s. So this means put your pencils down and the test is over. You don't want to hear this one twice. All right, so I'll just start. So there were the events. So memories are thought to be maintained by molecules that persistently enhance activated synaptic connections in neuronal networks. But our memories could last for decades, as my memories of these objects have lasted for decades. But the molecules themselves, in synapses, they last just sometimes hours and maybe just a few days. So this paradox, which was maybe first pointed out in print in this very brief one-page paper by Francis Crick in 1984. So this paradox has led some memory researchers to look for molecules that last 80, 90, 100 years. But the other possibility, which was mentioned by Crick, although not in this metaphor, is that it's possible that it's the interaction between short-lived molecules that is maintaining long-term memory. And so that's kind of like the metaphor of Theseus's ship. So Theseus killed the Minotaur in Crete and then saved the Athenians, who were going to be the best of Athens' youth, who were going to be eaten by the Minotaur. And so the ship that they sailed back from Crete to Athens, there was such joy in Athens that they preserved that ship for many, many generations. Now the thing is, the components, the planks, the oars, all had to be replaced over time. And so Plato and other philosophers basically argued about whether that was the same ship after hundreds of years or a replica of that ship. Now for us, the issue is simply what is the molecular equivalent for maintaining memory that's equivalent to the plank or the oar. And so from work that was done from many of the people in this room, we've established that there is at least one known molecule for maintaining long-term memory, which is a persistently active form of protein kinase C called PKM-zeta. Now I want to emphasize here the work of Ivan Hernandez, who really showed how this molecule has a unique function allowing it to be persistently active. So most forms of protein kinase C are dependent on second messengers. That's because they contain both a catalytic domain and a regulatory domain, shown here in the genome of in this case, the gene for PKC-zeta. But that regulatory domain binds second messengers and releases an inhibition of the catalytic domain. And so that's how the signal transduction, the short-term signal transduction works. But what Yvonne showed is that within the gene of zeta, there's an internal promoter that begins transcription, generating a messenger RNA that produces, when it starts to make proteins, only of the catalytic domain. There's no restriction on it. There's no inhibition. And so what happens is during LTP, long-term potentiation, which we'll hear more about in the next lecture, I think, or in learning, there's an activation of the NMDA receptor, calcium comes in, and a whole host of signaling molecules all releasing the translational block on this messenger RNA, and that allows for synthesis of the protein PKM zeta. The action of PKM zeta is to increase the number of AMPA receptors, which are doing the normal glutamatergic receptor transmission in excitatory synapses, shifting the distribution from outside to the postsynaptic density to inside the postsynaptic density. But the thing is, for this to work as a Theseus's ship kind of model, there has to be two things. One, there has to be a way to keep the level of PKM zeta, the steady state level, high for as long as the memory would last. Now, we've shown actually that in LTP can last for hours, the increase. In memory, it could last for a month. Okay. So that's one issue that has to be solved. But then there's another issue that has to be simultaneously solved, because information is thought, memories are thought to be stored as differences in synaptic weights, that some synapses are potentiated, but others of the 10,000 synapses in a neuron are not potentiated. So you have to have this persistent targeting of PKM zeta that's sustained. So how is that possible? Well, what we think it is going on is that PKM zeta is binding to another protein called KIBRA. And it's been known for many years that PKM zeta and KIBRA can bind together, and that causes a slowing down of the turnover of PKM zeta. It's also been known for many years now that KIBRA alleles are associated with either good or poor, but normal memory performance. So when we look for with immunocytochemistry, to begin by simply looking where the PKM zeta and the KIBRA are. So this is a neuron in culture. Here's one example. Here's another. And if you look at the postsynaptic densities using a marker, PSD95 in blue, you'll see that there are many, many PSDs. But there are only a very small percent of them that contain this postsynaptic protein KIBRA. PKM zeta is throughout the neuron, but is concentrated at the spines that have KIBRA. In fact, there's threefold more higher density of PKM zeta in the PSDs that have KIBRA versus those that do not. Now, it's important to realize that as a constitutively active kinase, it's not dependent on second messengers. It's the level of the kinase that's important, the level of the protein. So this means that there's a threefold higher activity of PKM zeta in the spine, in the synapses that have KIBRA. So then we looked at LTP. And so the late phase, the protein synthesis dependent phase, you could measure 3 hours after the tetanus here, where the LTP is initiated. And even though there are hundreds of signaling molecules that are triggered by this strong tetanic stimulation, almost all of them are over within minutes or half an hour. There are very, very few proteins that have been shown to change at a 3-hour time point. But PKM zeta is one of them. That's how we discovered PKM zeta back in the 90s. But now we see that KIBRA is also increasing. And if you look at where the PKM zeta and KIBRA, where they merge, where the signal is merged, which is indicating where they're forming complexes together, we can see that under basal conditions, which is a slice that we just stimulate with test stimulations for 3 hours, there's not that much co-localization. But then when you do LTP, we can see now that there are spines, many spines, that are having the co-localization of PKM zeta and Kibra. So this gives us a model in which we think that under basal conditions, there's very little PKM zeta and Kibra, so the levels are very low. Now during the induction of LTP, two things are happening. One is you get the early phase of LTP, a purely post-translational increase in the number of AMPA receptors, which doesn't require any new synthesis. But that shifts, by other molecules, the AMPA receptors into the PSD, which can then bind to the Kibra. And now the second limb of late-phase LTP is new protein synthesis of both PKM zeta, which we've known for years, and now we also find Kibra. So the Kibra binds first, and then the PKM zeta also binds. And because of the decreased turnover when the PKM zeta and Kibra are in a complex, that can persist, even though it's cycling in and out of the spine, it can have a persistent increase in the level of PKM zeta, which continues the potentiation. So how can we test this hypothesis? So what we did is, based upon the crystal structure of the atypical PKC, we, with a group in Florida, designed an inhibitor that would block the allosteric site where Kibra binds to PKM zeta. So the idea is, if this is the maintenance of LTP, if we block this part here, so there won't be any complex formation, there will continue to be turnover, and so the level of the AMPA receptor in only the potentiated synapse would reverse. And when we add the drug, that's exactly what we see. Reversal of potentiation, while a second pathway that was without tetanization was unaffected. Now, one of the things about PKM zeta that's known is that if you knock it out genetically, other PKCs take over that role. So we took advantage of that to do a pharmacogenetic experiment in which the prediction is, without the target for this drug called Zetastat, there would be no effect. And there was not. So we have additional data I don't have time to show, but we've shown that this drug, Zetastat, erases one-day active place avoidance memory. Maybe we'll hear some more about that in the hippocampus. We gave the drug and we told them to get knockouts as controls to a group in McGill, and they did fear conditioning, and when they broke their blind studies, again, showed the same effect on erasure of fear memory. Now the thing is, it's possible that something else unknown other than Kibra is binding to PKM zeta. So we made a second drug that inhibits the PKM zeta binding part of Kibra, and that did exactly the same thing as Zetastat, reversing late LTP and erasing memory. And so our conclusions are that long-term memory is maintained by two interacting mechanisms. One is the persistent synaptic potentiation by PKM zeta. We talked about that for a while. But second, what's new is that there's persistent targeting of this action to activated synapses by Kibra. And because the individual Kibra and PKM zeta molecules within the complexes can exchange, data I haven't shown you, while the sites of their interaction at activated synapses will remain stable. And thus, analogous to Theseus' ship, despite the turnover of individual molecules, long-term memories are maintained by continuous Kibra PKM zeta interactions. Okay.